So today we're going to continue on with our new nomenclature. This is talking about a certain kind of isomer. So remember we talked about last time, we'd introduced constitutional isomers. That was from before. Remember, same molecular formula, different configuration. Parts of the molecule are in totally different places. Then we talked about conformers. Those are things like staggered and eclipsing. These are rotation about a single bond. Last time we introduced stereoisomers. Stereoisomers are a special class of isomer. They're still got the same molecular formula, basically the same connectivity. What I mean there is parts of the molecule are kind of in the same region. The difference comes down to geometry about an immovable center. In this case, we started with double bonds. In a double bonding center, we can't rotate it, so the relative presentation of the four groups attaching to that center, could be hydrogen or whatever else, defines a geometry. Maybe. If they are different, and by different, we had a nomenclature rule. We call this what? This geometry, we have two letters we can assign to a double bond. It's either Z or, and what does that refer to? If we say something is Z, what does it mean? Yeah. It means that the two high priority groups are on the same side. Not the two largest, not the two ones that you like the most, not the two ones that just have the most molecules or atoms in it. It is based on priority. Priority is an assignment we use to rank them. Yeah?
Are Z ones higher energy?
It depends. Good question. Are Z higher energy than E? Not always. So remember, E and Z are strictly based on this priority rule. It's a molecular. It's based on the molecular weight, basically, right? The formula weight of an atom. Higher energy implies that two things are closer together. So you're right. For certain kinds, like if I had this molecule, where this is a methyl and a methyl, versus this molecule, the E one is going to be this one, where the two methyls are anti to each other, or opposite sides. We have another name for this too. Remember, the relative presentation of two groups across a fixed plane we can refer to as what? Trans, that's right. The two methyl groups here on the right are trans. The two methyl groups here are cis. In this case, yeah, this is probably going to be higher in energy, because it's kind of like it's eclipsing. But priority doesn't necessarily link to big, right? There may be a case where a fluorine or a chlorine, and back to the example we have on this screen here, the structure we've shown, this massive, weird alkene with these chlorines, we left off saying, okay, high priority group on this side was that guy. High priority group on this side, this was the thing that broke the tie. So this was a Z alkene. They're both on the same side. Even though the molecular weight, the size, maybe the steric volume of the bottom one may be bigger. So it's not directly linked to each other. Yes? Oh, thank you. Sorry, guys. All right. Now we're back. Okay. So we stopped with this one saying this is a Z alkene. What we're going to jump off now is the same kind of assignments. What about this one? Is this an E or is this a Z? So let's start on this half. Remember, we divide the molecule. We look at the two. We have, if we're doing sort of that game of war, this is a chlorine up top. This is a carbon. Which one wins? Chlorine. Chlorine. Okay, high priority group is down here. Let's do the other side. This is a, and this is a, okay, we're tied. You move out. What is attaching to the top position? We have a hydrogen, hydrogen, and at the bottom, we are out of atoms. We have a tie. This does not have an E or Z name. What we mean here is two things. First of all, if we're out of it and we can't make a decision, this would fall as neither. It is not E, it is not Z. What we're saying is, does this molecule have stereoisomers? No. If I were to take this methyl group and switch it with this methyl group, do I have a new molecule? Would it have a different IUPAC name? No. Same thing if I were to take these two groups here. If I were to swap those two groups, it's the same molecule. This is like taking this guy and doing a pancake flip. So if the two molecules have identical IUPAC names, or if they have two groups that we're evaluating, the CIP priorities are the same, it does not have any stereoisomers. This is why doing CIP is so valuable, is because it is discriminating. It goes through and says, even if visually it looks like there might be something, if you walk through a structure, even if it's presented in some weird conformer, if the CIP ranking is identical, there are no stereoisomers here. This is not E or Z. Okay, let's try this guy. You have two double bonds. So what's the root name for this? Longest carbon chain is, yeah, you got 7. That's going to be a hept. It has how many double bonds? 2. So it's not just a heptene, it's a heptadiene. Where are those double bonds on carbons number? 2 and 4. We've got an alcohol also on carbon number 4. So you can call it a 4-hydroxy 2,4-heptadiene. But we need one more piece of information. What's the geometry of those bonds? Do they have EZ isomers? So let's take the first one. First one here, we are looking at carbon versus hydrogen. Carbon wins. Okay, let's do the other side. Carbon versus hydrogen. Carbon wins. We definitely have two priorities. This double bond here is called a Z, right. Let's do the other one. Second one, we have oxygen versus carbon. Who wins? Yeah, oxygen wins. Oops. Other side, hydrogen versus carbon. Carbon wins. So this second bond is a E. We have two geometries. One is a Z, one is an E, and most importantly, this Z bond is the 2. The alkene that starts at carbon 2 has a Z. The alkene that starts at carbon 4 has an E. So these go out just like before. If we'd finished the name, if we put all the numbers, if we have all the structures on top of it, we add the letter associating with the geometry out front of the name, so it would be an E something. Since we have 2, we need to isolate, name both, and their relative positions. The 2 position is a Z, the 4 position is an E, and then you have the rest of your name. Yes?
Does it matter if the E and Z are alphabetical?
No, usually when you put those 2 out, numerical. So you list them out, the numbers or the letters associated with isomer geometry out front are 2, 3, 4 numerically with whatever number goes along with it. Yep. At least by convention. I don't think I've ever seen alphabetical up front with those. Point is, it's trying to go back and remember what you're saying is the double bond at position 2 is a Z. Double bond at position 4 is an E. So this would continue. If you had 15 bonds, you'd have 15 letters with numbers associated with each. Just like saying where the double bond starts, the number associates with the letter going into each of them. Okay? Okay. The one last thing to remember, E and Z notation is limited specific to alkenes. They're only useful when we have the ability to say, look, I have a plane divided by this alkene. I have 2 priority groups on one side of the alkene, 2 priority groups on the other side. That allows you to give it an E or Z. The nomenclature we talked about, the sort of more informal relative nomenclature in terms of cis and trans, that is a sort of a generic point. That's like saying I am standing to the left of this desk. You can use cis and trans for both rings, like cyclohexanes. You can use them for alkenes. Do not use EZ geometry on cyclohexanes. E and Z is restricted to talking about isomers only for alkenes, okay? So it's specific to that. That's alkenes, yes? A cyclohexene you could. If it's talking about a double bond and the geometry in a double bond, that would be okay. The nice thing though is if you had a cyclohexene, depending on what the substituents are, these two will always be carbons, right? It's always going to have this kind of geometry in this case. But yes, you could, if you wanted to talk about, let's say if this was a chlorine over here and a hydrogen, this would be chlorine is highest priority, carbon is highest priority. That double bond would be considered an E double bond, just because the two high priority groups on that center are across that double bond in that sort of case. But yes, again, what I mean by about do not use it on cyclohexanes, if we had down OH, down methyl, these guys are trans to each other, there is no EZ that you can use in this sort of a case. This is not an EZ naming convention. Cis, excuse me. These guys are cis, same side. So that's the world of sp2 stereoisomers. If we have alkenes, that's where we start off. The one other kind of stereoisomer comes from the sp3 center. This is what we actually emerge into a special property we're going to talk about, which is called chirality. When we start to break out into the three-dimensional plane, away from this sp2 planar type structure, we get a new kind of stereocenter we call an asymmetric center. These are special because the consequences of this center has massive implications for biology, for three-dimensional geometry, molecular properties. This is different, so it gets a very, very special name. Just like in the first case, alkenes, the properties, the boiling point of a E-alkene and a Z-alkene can be radically different. So that's why we have to have this priority and talk about which one we're dealing with. Just on this point before, on alkenes, before we jump away from it, does anybody remember the conversation in foods about trans fats? Yeah? Of the two geometries I've drawn here, of my alkenes, which one would you call a trans alkene? A or B? A. Why is that bad? Trans fats taste delicious, right? But what is it? Do you remember? Does anybody remember why trans fats are bad for you? Yes? Exactly. Basically, if you look at a trans alkene, long-chain fatty acids, the things that make up the lipids in your cells, trans fats, these long alkane chains with this double bond here, they pack exceptionally well. Do you guys, butter? Yeah? Interact with butter? What about vegetable oil? Well, no, come on. But you know the properties are different. The molecular construct, what makes them up, are very simple. They're similar. Butter is made up of a lot of very linear structures, straight lines. Vegetable oils have unsaturated, and more importantly, cis unsaturated systems. Those kinks mean that the molecules don't pack as well, they remain liquid. They're easier for your body to absorb, they're easier for your body to digest, they're easy for your body to break down. If you start having a bunch of things of these trans fats, what happens is they're much easier to store in certain ways. Your body treats them differently just based on this geometry. Geometry is huge because that completely changes both physical properties but also how you interact with them. This is even more. When you start branching out to a three-dimensional center, I have my right hand. Can I shake your hand? Would you be cool with that? If I'm going to a party, I'm meeting my new friend is Corey. Right hand to right hand, that worked, right? Okay, I'd like you to extend your left hand. This is the weirdest handshake in the world. The molecular geometry of a shaped object that has a shape is very easy to recognize other things with a shape. This happens all the time in biology where you take a molecule, a drug, and how it interacts with other chiral objects. You are a three-dimensional object. Three-dimensional symmetry matters. So this is why we give it a special priority name as an asymmetric center. This is a kind of stereocenter. So by definition, anything, any carbon that creates stereoisomers, we call it a stereocenter. Carbons that create this sp3 shaped stereocenter, gets a special name. It is an asymmetric center. So all carbons that create stereoisomers are called stereocenters. Only carbons that are sp3 tetrahedral that have this particular geometry, we call asymmetric centers. What I mean there, if I had this carbon, where this is a methyl, this is a hydrogen, this carbon here, this is a methyl, this is a hydrogen, this carbon is a stereocenter, as is this one. That carbon is the point where if I were to switch this group and this group, I get a different stereoisomer. So the carbon that is holding onto the group, where changes at that carbon, switching any two bonds at that carbon, where a new stereoisomer arises, we call it a stereocenter. Both carbons on the ends of an E or Z alkene are called stereocenters. Asymmetric centers are specifically tetrahedral centers, where once again, we have, let's say, a methyl, a hydrogen, an ethyl, and a chlorine. 4 different priority groups at a tetrahedral center. This is a stereocenter, but it's better than a normal stereocenter. This is an asymmetric center. It gets a special name priority. So that's why we say that, look, any center where if I was to switch 2 groups, in this case, if I switch these 2, I'm going to end up getting a new molecule. Ethyl goes back, chlorine comes to the front, methyl top, hydrogen at the bottom. These are not the same thing. By simply switching those 2 points on this tetrahedral center, these 2 molecules are stereoisomers to each other. It happens when the stereocenter is this tetrahedral center. We give it a special name. It is an asymmetric center. So now I'm going to prove to you this whole thing about these are not the same thing. First of all, if we have to identify an asymmetric center, finding them in a molecule means we're trying to find an sp3 carbon with 4 different priority groups attaching to it. They cannot have the same priority. So if you're given a molecule like this, the first thing to do is scan through it. This is the same behavior that you did when you're looking for functional groups. You started the molecule, and we walk along the sigma bonding chain, and your eye should stop at places where there may be a stereocenter. Here, could that CH3 ever be an asymmetric center? Why not? All the H's are the same. It's just like the alkene we showed you before with 2 methyls. All the hydrogens attaching to that center have the same priority, not an asymmetric center. What about this guy? Is that an asymmetric center? Why not? sp2. It's flat. We need to be an asymmetric center, has to be tetrahedral, sp3. So that's out. What about this one? We got different carbons, right? The carbon to the right and the carbon to the left will have different priorities, but it has 2 hydrogens attaching to it. Those have the same priority. They're out. Your eye should be drawn to places where at least 3 lines attach when you're looking at a center, right? Those are the places where there's at least 3 carbons or a hydrogen and something else. If you have a CH3, a CH2, they're out of the running right away. sp2 centers, don't even bother. Oxygen, doesn't matter. You're looking for carbons that are sp3 hybridized with 4 different priority groups, which means these are not even in contention too. This is the only one that might be possible. So the question we have to ask now is, are the groups attaching to them, can I assign different priorities to those centers? All right, I'm going to fill this part in. Hydrogen. So we have hydrogen. That has 1 priority. No problem. It's going to be the lowest priority group. We have carbon, carbon, and carbon. At this point, all 3 are tied, right? So now we ask the question, what is attaching to each? Up top, the 3 other things are hydrogen, hydrogen, and hydrogen. To the left, this is attached to a carbon, hydrogen, hydrogen, as is this guy. Well, at this point, if this was the lowest priority group, I'm going to give that a number 4. Up at the top here, this is the next, number 3. The reason why he's lost out, his hand, the cards he's holding, just hydrogens. The other two are at least holding one carbon in that point. Number 1 and number 2 are down to this left and right. We need to go out one more center. The next round out here, it's carbon versus carbon. On the left, this carbon here is, what are the 3 things attaching to that carbon? Remember, you count away from the center you've been looking at. There are what attaching to him? Yeah. And? Remember, double bond counts oxygen. So it's actually oxygen, oxygen, carbon. The other side we have hydrogen, hydrogen, hydrogen. Who's the highest priority group, left or right? So this is number 1, this is number 2, 3, and 4. We have 4 different priority groups. That center is an asymmetric center. So we can identify it first by looking through the molecule and finding sp3 carbons with at least, visually, you're looking for 3 lines, at least. If you have only 2, there must be 2 hydrogens there. Don't even bother. Next thing is, now we go through and we do our CIP rules. Same way we did with our alkenes, but now you're walking out in these 4 different directions based on this attachment point. So that is it. What about this guy? So, like we just said, should I even look at this center? Nope. What about this? Here. These as well. The only thing you should kind of focus in on is, does that center and that center? Those are the only 2 that might be asymmetric centers. They're the only ones that have at least not 2 hydrogens or 3 hydrogens attaching. Okay, but are they asymmetric? Are the groups attaching to them different priority? Let's start here. I have a hydrogen. Cool. I have carbon, carbon, and carbon. Hydrogen, hydrogen, hydrogen. Hydrogen, hydrogen, hydrogen. These are the same, not an asymmetric center. If we do the other one, standing here, once again, I've got a hydrogen sticking out. That's great. But up top, once again, carbon with 3 hydrogens, carbon with 3 hydrogens. These are the same. Just because something is drawn with a wedge or a dash does not make it an asymmetric center. You're just showing geometry. You're showing that, look, it's a tetrahedral center. A methyl must be back. A methyl must be forward. It doesn't make it asymmetric, though. Yes? All 4 need to have a different priority. Basically, what we're coming to is, I need to assign 4 different priorities in order to come up with a notation similar to E and Z. We call it R and S. If 2 groups have the same priority, doesn't have any notation, it's going to be the same. The other way to test this is, would you make a new molecule? If I were to take that methyl at the bottom and this one at the top and switch them, is this a different molecule? No. Same priorities, same molecule, same IUPAC, not an asymmetric center. So this one has no asymmetric centers. This one has 1 asymmetric center. Okay. How many here? Yes?
So are they called asymmetric centers because they're literally asymmetrical? Like all the functional groups would have different sizes, so on the previous molecules they would have the same sizes?
Exactly. They're asymmetric because by changing this group, you create a plane of, or you break a plane of symmetry, basically. That's why they're defined as an asymmetric center. They change the overall symmetry operation on the molecule. Same methyls, doesn't matter. It doesn't matter which way you look at the same molecule in both cases. Okay. Yes? No, they do not. We cannot give a priority to a lone pair, right? The lone pair is just lone pair. Priorities are given only to atoms. So lone pairs are not counted as an asymmetric center. Yes?
So if it's not an asymmetric center, then, or if it doesn't have them, what is it?
If it doesn't have any asymmetric centers, the molecule will not have any stereoisomers. It is what we call a symmetric molecule, or again, there is no stereoisomer in the molecule. Having a stereocenter means the molecule will have stereoisomers. Okay, show of hands. Who found 1? Sorry, question? Okay, cool. Who found 1? Oh. Who found 2? 3? 4? 5? 6? 12? Yeah. There should be 5. The way you look through this molecule to identify them, if we start over here, you've got nitrogen. Don't care. Why can I eliminate this entire ring? I'm not even going to look at it. Why?
sp2.
It's all sp2. Here I've got a CH2. That's a nitrogen. Don't care. CH2, CH2. You begin moving quickly through the molecule, focusing only on places where there's at least a couple of bonds attaching. So you can stop and evaluate this center here, this center here, 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 and here. Those 5 positions turn out to be the asymmetric centers in this molecule. Now granted, each of them you'd have to stop and say, wait a minute, are those 4 different priority groups? You'd have to work out the CIP. Yes?
But the one on the right-hand side, how do you count in that?
So for this one here, you literally start at that one and work your way out single atom at a time until you break a tie. In this case, if you started here, so this is a good one. Let me do this one specifically. Okay, so I'm going to start here. We have nitrogen going to the back, hydrogen over here, carbon, down here, carbon. We've at least got 2 now, right? Nitrogen is going to be number 1. Hydrogen is number 4. We're kind of tied for who's in 2 and 3. At the moment, we've got carbon and carbon. Okay, what is attaching to this carbon down here at the bottom? We have oxygen, carbon, and, yep, up top, what are the 3 atoms attaching to this one? We have, yeah, carbon, carbon, carbon. So, can we break the tie?
Yeah.
Which one, top or bottom? That's it. Just because it's in a ring, do not fear. We can break the tie at that first position. This first hand, carbon, oxygen, carbon, beats carbon, carbon, carbon. And we're done. Now we have number 2 is in this lower position, number 3 over here. Same thing for each. So as complex as it gets, work through strategically and slowly, away from that center. So these are our 1. How about the maximum number of stereoisomers? If you have 5 stereocenters, how many stereoisomers could this have? There's 2 to the n. 2 to the power of how many centers? Each center can have 2 geometries, right? The relative to position, every asymmetric center gives rise to 2 possible stereoisomers. If you have 5, 2 to the power of n, where n is the number of stereocenters, that's the maximum number that are possible. 5 stereocenters, there's 5 possible combinations. This is like digital logic. 0 or 1, and you have 5 individual positions. Each can be a 0 or 1 in each point. Now, we're going to talk a little bit of a symmetry operation. That can be reduced. There are reasons that because you have, let's say, 2 or 3 stereocenters, 2 or 3 asymmetric centers, you may not have that full 2 to the n power. Okay, now if you look at these 2, what's the difference between this pair of molecules? Do they have stereocenters? Yes?
Oh, I was going to say on one, the hydrogen is going into the page, on the other, out.
Exactly. The main difference, if you look at them, the name would be similar, right? They're both what kind of a molecule? They're both longest carbon chain. Yeah, 1, 2, 3, 4. They're both butanoic acids. They're both methyl butanoic acids. The difference comes down to the geometry at this center. One of them, hydrogen's to the back. The other one's methyl is to the back. These guys are actually mirror images. If you were to try and line these up, these are like your left and right hands. As they're drawn here, through this plane of symmetry, it's harder to see. You see methyl to the front or the back. But that's kind of looking at, if I look at my left and right hands, it's like lining them up this way. Methyl is one way, methyl is the other. you're lining up the two molecules like this. So if I were to just turn it this way, take one of those molecules and rotate it out through a plane of symmetry, you'd notice these guys are actually mirror images to each other. So in order to come up with a name, just like E and Z, we have a convention for asymmetric centers we call R and S. R stands for to the right. It doesn't, but it's R is to the right, S to the left. I know S stands for sinister because, again, everything in organic chemistry is based against left-handed. My brother is left-handed. We used to tease him about this all the time. Left-handed people are evil, I guarantee. But what you're talking about, to the right or to the left, is talking about the direction of rotation, clockwise or counterclockwise, when viewing one of these centers. What you have to do is assign priorities 1, 2, 3, 4. That's the first step. Then you orient the molecule such that the lowest priority group is away from you. This is like looking at a Newman projection of your sp3 center. Once you've done that, the Newman projection looks up where the lowest priority group is to the back. You're now staring at the center, 1, 2, 3. Your two choices are, if counting from 1, 2, 3 with that number 4 group to the back, if that is a right-handed rotation, then it is to the R. If it's left-handed, counterclockwise, it's S. The way I used to think about this too, put your hand, reach out, grab the steering wheel. So we're on the red structure. I'm grabbing the steering wheel at number 1. I'm really good at driving. I only need one hand. If I'm making a right-handed turn, I go to the right. If you go from number 1 to number 2 and you turn the wheel that way, you will make a right-handed turn. If I start at number 1 and I turn the wheel to the left, I will make an S. R rotation is this right-handed clockwise. S rotation is counterclockwise. The other one too is nobody but you. Wonder Girls, thank you. Same thing, totally works. Whatever helps you remember it, use that mnemonic. The fun thing about doing exams in person too is I guarantee you guys are going to be sitting there doing this. Eyes closed. So, for the molecule we just showed here, this chlorine, bromine, fluorine. Step 1, we assign priorities. Bromine gets the highest, chlorine gets the next, fluorine is number 3, hydrogen is number 4. How you assign the numbers, that's just based on CIP. It doesn't matter how it's drawn. The most important next step is moving, twisting, turning the molecule to have a single perspective. Why this is so important is by identifying point number 4, you have to redraw or otherwise orient the molecule in a common location. The reason why for this is if we're trying to assign this as right or left, depending on your perspective, it can look like either. That's why we have to define a common point of view. We say we're viewing this along from this position down this carbon-hydrogen bond, or from this way down this carbon-hydrogen bond. We're just talking about a common view for this so that we can get a single geometry. If we look at this perspective, this would be the sort of Newman projection we would look at. Now we can look at this and say, oh, this is to the right or to the left. It's from this perspective here. So let's do this. Is this an R or is this an S? Or neither. Remember, just like E and Z, if you cannot assign CIP, if they're the same, it's not an asymmetric center, does not have any stereoisomers. So, highest priority group is? Yeah, so we're going to give that a number 1. Lowest is? So we're already in a good shot. We got 2. The next 2 groups, carbon and carbon. This one has 3 hydrogens attaching. This has a carbon and 2 hydrogens. So number 3 is? Yeah, this is number 3. This is number 2. As it is drawn right now, the hydrogen is already to the back. We're already in a good position. So looking at this as it is, hydrogen goes into the plane of the page. We could stop right here and say, okay, I'm looking at this 1, 2, 3. This is what? RS. That's an R center. The other way to look at this, and this is why having one of these guys a tetrahedron built up is so, so important. If we start off with our molecule, we can say, all right, I'm going to just by design, highest priority group for me is always going to be red. Lowest priority group is always going to be this sticky little bond, so that's why I'm holding it by that position. 2 is always going to be green. 3 is always going to be blue. You choose your color scheme, but 1 is red, 2 is green, 3 is blue, lowest priority group is there. So by having this and looking at your molecule, you can reorient, move these around so that you have set this up in that geometry. The way that we drew it before, we had something that looked like carbon 3 and 2, as drawn, were both in the plane of the page, so these guys are flat here. To the back was my hydrogen. To the front was my fluorine. So we were looking at it in this kind of perspective. This was a dash. Up here, my fluorine coming out of the page is a wedge, and then my 2 carbons are in the plane of the page. So from here, it's already kind of okay, but what I'm trying to do, that Newman projection, is grab the lowest priority group, point it straight at it, and count. 1, 2, 3. This is to the right. So having something like this as a quick point of reference allows you to move and manipulate the molecule very quickly if you're having problems seeing it on the page, really, at that point. That's number 1. What about this? RS. Okay, highest group is, highest group is bromine, lowest hydrogen. Make one note, the lowest priority group, as it is currently drawn, is pointing towards you. All right, so just pay attention to that. What you're seeing is you're looking at it from the opposite perspective. You need to do your assignment. Still okay. What's number 2? We've got carbon and carbon. We're tied. This has carbon and 2 hydrogens, as does this. At this step, we are still tied. I have to move out 1 carbon. And again, I know that you guys will get faster at this. Some people could quickly look at this and go, oh, propyl, the 3 carbon, is going to be higher than the ethyl. Just for now, too, go slow, be careful. Don't look at this and go, wow, there's a lot of carbons there. It's probably going to win. But in the case here, carbon versus carbon, this is carbon, hydrogen, hydrogen. This is hydrogen, hydrogen, hydrogen. This will win at that second center, making this 2 and 3. Okay. As it is drawn, if I counted from 1 to 2 to 3, what direction of rotation does that currently look like as it is drawn now? This looks like it is to the right. It looks like it's going to the right, but hydrogen is towards you. So if it looks like it's to the right, hydrogen is towards you, it's actually the other way. Well, I got that back, right? It looks like it's, did I do that right? There we go. There we go. Mirror image problem. Point is, your perspective here is reversed because you're looking at the lowest priority group. This is where if I had here and I said highest was number 1, number 2 is my blue, number 3 is my green, and I'm currently looking at the lowest priority group. It's pointing towards the camera. So if I looked at 1, 2, 3, it looks like it's an R. Lowest priority group is towards you. If you invert that, go the opposite direction. We're looking at it from the back. What used to look like an R center while the lowest is towards you is actually an S center. So for these ones, if lowest is towards you, you can assign it. So in this case, it looks like it's A. To the right, looks like it's R. But, oh, sorry. Invert it. It's an S. The reason I put this out is there are 3 possible common perspectives of any of these ones. If you're drawn right now in 2D line bond structure, the lowest is away from you, that's fast. Assign them all, lowest is away from you, what you see is what you get. The lowest is towards you, assign it, and flip it. You're looking at it from the opposite perspective. You're behind where you need to be. So you can assign this as 1, 2, 3. Looks like it's R, but I will actually have to turn the whole molecule over. It's actually an S.
Could you also like use your like thumb as like the direction of the hydrogen?
You can, exactly. It's much funnier if you have swinging arms. But yes, good point. If you say the lowest priority group is your thumb, if you are curling around to the right or to the left, then that can give you that geometry too. Whatever mnemonic helps you. Again, that's why I always rely on my tetrahedral centers. The last one. This is the hardest geometry to pick up easily. So, what's your highest priority group? Okay, chlorine is number 1. Lowest is hydrogen. Notice here, the lowest priority group is in the plane of the page. So these are the 3 possible combinations. Lowest is away from you, lowest is towards you, or lowest is in the plane. If lowest is in the plane, we're going to have to do a little bit more mental gymnastics. Number 2 is going to be my ethyl group. Number 3 is my methyl. 4 is your hydrogen. If you get this case where hydrogen is in the plane of the page, do not just count, oh yeah, 1, 2, 3. This is completely at some skewed angle. Remember, the way I have to cite this would kind of be like from this perspective. I would need to look as if I'm standing in the plane of the page towards that hydrogen. So the way I would imagine this is, I'm standing in the page, I think of this where I take my chest and I point towards the center I'm looking at. The hydrogen is now behind me. If I do that, I'm standing and looking at this, coming out of the plane of the page. That is my right foot. That is a methyl group. Into the plane of the page. That is my chlorine. Sticking straight up towards me is number 2. So number 2 is here. Out of the plane, number 3. Into the plane, number 1. 1, 2, 3. This is a what center? R center. So I have to cite this way. The 2 ways to do this is mentally imagine it from this perspective where you're looking at this geometry. Or you can redraw it. If I was going to redraw this, what I would do is you imagine that this molecule, what I have to do is I need to rotate this bond. If I were to simply rotate this bond, where now the hydrogen was to move to this position, the chlorine will move to this position, the methyl will move to that position. The reason I chose that is I pick whatever bond, not the lowest priority, that's in the plane of the page, and I'm going to rotate that center accordingly. So let me redraw that. I start off here. The hydrogen now moves here. What was in this position, number 3, has moved around to this one. This is my number 3 center. That's my methyl. What was the chlorine is now moved up here. This is number 4. 1, 2, 3. What does it look like? R center. Yes, sorry.
This is kind of a digression, but if say it was a hydrogen on the wedge instead of a methyl, this wouldn't be a stereocenter, right?
If both were hydrogens?
Yeah.
Yes. If they are both hydrogens, there's no difference in rotation or in CIP, no stereocenter. Just because it's shown as a wedge or a dash doesn't mean it is. They have to have 4 different priorities. Absolutely. So your 2 choices. 1, mental gymnastics, imagine positioning. 2, take the bond that is in the plane of the page, rotate the molecule according to that. It's redraw the structure where I'm moving or indexing those ones. Or number 3, much more helpful, get your model kit. If this was my model, once again, I'm going to put what I said, number 2 is going to be my green one. My lowest priority group, this is my methyl. I'm putting those both in the plane of the page. The chlorine, highest priority, is back here. Blue, methyl, coming out of the plane is right here. So in the plane of the page right now, I've got my lowest priority group, my hydrogen, and my ethyl group sitting right here. What I have to do is look at it from this perspective. It's like you're starting out here where these 2 groups are both in the plane of the page. We need to rotate it in this direction. Having this set up in this point where I can physically hold on to group number 4 and turn the center so that I can see it this way is a really, really helpful thing to practice with. So again, really encourage, if you're having any problems with the geometry of drawing things like this, or it's again mental picturing this, your model kit is your essential feature because it allows you to manipulate this here. But you're always trying to do, hold on to the lowest priority group and turn it. So it's just about using and practicing this. So for a note of that too, going into the final, the most heartbreaking thing I think I've ever seen in the final is somebody showing up with a model kit with the cellophane still on it and opening it up in the final. That is way too late. Practice now and again. All you need are a couple of these particular ones. You can even put with a Sharpie on it 1, 2, 3, 4 on a couple of atoms and move them and use them in that way. You're totally fine with that sort of perspective too. But I mean, get used to using it now. It's just like if you show up in your exam with a brand new calculator you've never used, not a good time to learn how to use the calculator. Okay. What about these two? Oh, sorry, yes?
Sorry, in the exam they talk about, like, for the model kit that it has to be disassembled and unmarked.
Yes.
So would you be allowed to mark it in the exam?
You can color them, yes. In the exam, if you wanted to put numbers on it, that's fine.
Okay.
Again, disassembled, we don't care about that so much. If you bring in a tetrahedron pre-built, that's fine.
Okay.
Don't bring in Taxol, like fully whatever, but this is okay. There's nothing wrong with having a cyclohexane and a tetrahedron just built up like this. They're basic kits. It'll take you a couple seconds to do. We don't care if you come in with it. Do not, what we mean by unmarked, don't show up with this weird oxygen that somehow has like Henderson-Hasselbalch equations written on it. I won't care about that, no. But if it looks like, yeah, oh, what's going on in my oxygen here? Well, in microprint, I've actually taken all the exam. Like, okay. What about these two? Okay, so first of all, we've labeled them 1, 2, 3, 4. Is that an asymmetric center? What about the other one? They both, these two molecules have asymmetric centers. So first point, asymmetric centers are a property of a molecule. A molecule can have asymmetric centers. Left and right, the comparison between the two, are these the same molecule, different molecules, stereoisomers? Do they have the same RS geometry?
Yeah.
1, 2, 3, 4. Remember, this is the one I'd have to look at from that perspective. What would this be? Is this R or this S? 1, 2, 3, this is a S. Okay, over here, 1, 2, 3, that is a, is it? These are both S. What you're doing, again, let me show you how you go between those two. Imagine, the first one we did, again, I'm holding onto bond number 4. Bond number 1 is up. Number 2 is towards you. Number 3 is to the back. That is the molecule we had on the left-hand side. So if I were to turn it this way, that's an S center. Okay, to show the other one, 2 was towards you and down versus 3 is to the back and up. How do I convert it? Here. This is still up. The number 2 position is up and towards you. The number 3 position is to the back. The difference between those two is just which way I position these two. Blue versus red versus blue and red. It's just an orientation change. I haven't changed anything about the molecule itself. All I've done between these two, 2 and 3 versus 2 and 3, is looking at it from a perspective like this. Nope, nope. Perspective like, man, that's hard. Like this versus this. You're doing just a small rotational perspective between the two. Number 2 is always towards you. In both cases, 3 is always to the back. The plane of the page is defined by carbon 1 and 4. So it's just an orientation difference, not a change in R and S notation. What about this? RS. What's the highest priority group you can see? Oxygen. What's the lowest priority group? Now you're left with a methyl and a methyl. Do they have the same priority?
Yeah.
Does it have R and S?
No.
No. Does this have any asymmetric centers?
No.
If it doesn't have a tetrahedral carbon with 4 different things attached, no asymmetric centers, No stereoisomers. This is just a simple molecule. We're drawing it with geometry, not a thing. Last thing. How do you name this? You don't. No, yes, you can. Okay, let's do it quickly. What's the base? How many carbons? So it is a butanoic acid, right? This is a butanoic acid. We have 2 chlorines, so this is what type of butanoic acid? This is a, yeah, this is some dichloro. They're on carbons number, yeah, it's a 2,3 dichlorobutanoic acid. The last thing we'll have to do is assign this as R and S. So, 1, 4, that's going to be number 2. Is it? Actually. So again, I totally fell into my own trap. You have a carbon and a carbon. This guy over here has oxygen, oxygen, oxygen. This one has chlorine, carbon, hydrogen. Which one wins, left or right? This guy. Just because, wow, 3 oxygens is so great, chlorine beat oxygen right here. That's number 2. This is number 3. So we'll finish on this point. We'll do the last part of this naming, but this is what I mean about sequential practice. I'll see you guys on Monday.